So welcome back. Unless you've been living under a rock, you've noticed that one of the biggest things that happened to MPC in the last few years, this notion of pseudorandom correlation generators. And so finally, we have a talk about this by Lisa Kohl, who is one of the main people involved in this very exciting line of research. So we're very happy to have her participate.
Thank you so much. Thank you so much for the invitation. So yes, I'm gonna talk about correlated PCGs, correlated pseudorandomness from expand accumulate codes. Will be at least some part of my talk. And this is joint work, it's very recent joint work with Ilad Boyle, Geoffroy Couteau, Niv Giboa, Yuval Ishai, Nicolas Resch, and Peter Scholl, who unfortunately all couldn't be here today. And this is particularly special for me because TPMPC was my first workshop I've ever visited in the crypto community, just a couple of I think even weeks into my PhD. So you find me here hidden a bit in the back, and so it's so nice now to see so many familiar faces in the audience, and especially after having a long break. And if you look a bit more, you will also find quite a couple of the other co-authors. So it's so young. Yes. We are too, but that's those last years. So it's very nice. So to have seen, I think PCGs are even mentioned in the very first talk of this workshop. But since I'm giving the first talk, and I don't assume everyone is familiar of like kind of the magic behind it, the first part of my talk will be basically a PCG tutorial. What is it? Why is it cool, and how can you construct it? And then the second part, I want to talk about a bit about the recent work. And so we start from the very beginning, Crypto 101. If I want to securely communicate, what can I do? Well, the simplest thing I do is, right, if two parties have a joint key, have like a one-time pad, then they can use this, and Alice can encrypt her message with the one-time pad, send it to Bob. Bob can decrypt the message and get the ciphertext. If only the two, the one-time pad, that's perfectly secure. And that's a form of correlated randomness. That's just like here, the correlation is just equality. And of course, I mean, this is not a very exciting correlation. What we actually do, like here for in this workshop, we want to compute, right? We're here for secure computation. And in this talk, I will only talk about secure two-party computation. I can already mention that here. And so imagine now Alice and Bob, they want to compute like a secure end. They have a value X and they have a value Y, and they want to securely compute the end. And now they need they need something a bit more involved. So what, for example, they can use is if Alice has a tuple B and MB, and Bob has both M0 and M1, but doesn't know, kind of each doesn't want what the other party exactly has, except for that they satisfy this correlation. This is just, I mean, you will recognize this is just a UT correlation. Then it's very easy to do the secure computation. It's very much the same, almost like it looks very similar even how you do the secure communication, right? You can just use, Alice can use the bit to blind her input, and then Bob can use kind of the message he got by Alice together with his own message to blind either his value or just send a random value, and then Alice can construct the output. So if we have a bit more complex forms of correlated randomness, so here this is the OT correlation, then we can not only securely communicate, we can securely compute. And you can also consider this. So I will mostly talk about F2 in this talk. So you can think whenever a talk says something about F2, but you can also consider this. You can rewrite this and consider this over larger fields, basically as OLE, or Lewis linear evaluation correlation. And so why correlated pseudorandomness, or what are PCGs good for? So typically we need long correlated random strings. We have a lot to talk about. We have a lot to compute. So in secure computation, it's also Crypto 101, your random string has to have the length of your message. Well, that's not really what you do, right? You don't exchange a super long string, what you do is you exchange a short seed, I don't know, 128-bit, and then you use you use a pseudorandom generator, you use a pseudorandom, like you just extend it and use it, you have secure communication for lifetime after this one short setup step. And this is something that we know and we do, and it's just the state of the art. And for secure two-party computation, it's similar. So for example, we can compute any kind of circuit, but we need 2 OTs per AND gate in the circuit. So if we have very complex circuits, we will need a lot of the randomness. And traditionally, what we settled for was kind of, okay, this is very expensive, let's just push it to the pre-processing phase. And then in the pre-processing phase, we have like huge communication, not even like the number of AND gates, but the number of AND gates on top, and then with secure communication on top, with secure computation on top to do it securely. And what I want to talk about in this work is how to kind of get to the world where we are with secure communication in some sense, that we only have to exchange a short seed once and then can use pseudo-random correlation generator or pseudo-random correlation function for basically unbounded stretch and iterative stretch. And this is really something very recent. So this is the line of research that just started a couple of years ago. And yeah, why is there such a difference? The difference is really the correlated randomness. There's this correlation, and it's much more that's much more involved to generate, to compress. And so how to compress correlated randomness, and that's where the pseudo-random correlation generator comes into play. For correlation, it's always, you consider it always respective to a fixed correlation. You can, for the talk, only think about just this OT correlation. It gives you secure computation. And what it looks like is now we want the same that we have for pseudo-random generators. We want the parties to have short seeds and they can expand it to long strings. And so the PCG is formally consists of a generation algorithm and expansion algorithm. And so if we sample a pair of correlated keys, then we want, of course, if we expand it, that we actually get something in the correlation. Otherwise, it's not useful. So for example, we want n tuples in the, for example, n OT tuples, where just every OT tuple is looks like a new, fresh, random OT tuple in the correlation. And I already said random, so we want pseudo-randomness. If you just look at one half, it's pseudo-random. And if we look at equality, if we look at pseudo-random generators, then we're done. This is all we need. We need correctness, we basically only need pseudo-randomness. But here we need something more, because here the secret is actually against the other party who has some partial information, of this compressed seed. So we need that even if I have my seed as say Alice, then the output of Bob should still look like a fresh random tuple in the correlation. So I learn nothing more than, okay, what Bob, what the other party has is in the correlation. And once I have that, well, then I can, so there's no secure computation there yet, but now I just have to set up in the pre-processing phase, I just have to set up these short seeds securely, which makes it efficient, even if you do it generically, because they're very short. And when you do it with dedicated, this is very, very cheap, and you get malicious security at very cheap price. And then the rest of the pre-processing phase is just silent expansion. The parties don't talk to each other because we have this PCG feature where you can locally expand. And then the online phase, we can just do fast information theoretic secure computation. So I will just talk about the first part in the rest of this talk. And so, okay, so this is already something. So how do we construct PCGs? And a simple warm-up, just for the purpose of getting familiar with the definition, assume we just want for the equality correlation, and we know that we can get this from pseudo-random generator. So this pseudo-random generator should give us this. And yeah, this is very easy to instantiate. What do? We just give both parties the same seed. And then let's look at the definition. Well, the correctness says every tuple has to be in the correlation. Correlation is equality. I get the same seeds, I get the same output, so this is fine. This is fine. Pseudorandomness, well, pseudorandomness, this is just a requirement from pseudorandom generators, so we're good. And now security, the other party's output looks pseudorandom up to correlation. Well, there's no, the other party has the same seed, there's no randomness, this is just trivially satisfied. And this is where the difficulty comes in if we want, if to get security, if we're interested in more general correlations, for example, oblivious transfer correlation. And so what we want is we want to, PRG seems good, we want pseudorandomness, something else, some magic happens and we get a PCG, it's like say PCG for OT. And how do we get there? We need a bit like a larger toolbox. So we've already, I mean, secret sharing, I assume everyone is familiar, but it will be the starting slide for the next slide. So secret sharing, we just want that individual shares hide the secret. We want, if we combine the two secret shares, we can recover the secret. And we also want some kind of succinctness. Our shares should not be much, much larger than the value we want to share in order to be useful. And the simplest example is just additive secret share. And what we need in this talk, and this is actually the key ingredient to getting PCGs, is you can say is function secret sharing. And in function secret sharing, instead of an element in a send, we want to share a function in a function family, in a family of functions. And we want to share it very much the same way that we want to share value. We want to share it such that if I just have a key, then that should hide the function. Then I want some correctness. So I should be able to, the party, so this is a function taking an input, giving an output. So if I just want to validate on an input, I should be able to do so giving the keys. And the requirement that's very useful in a lot of settings and especially for PCGs is that I have additive reconstruction. So that for every X, I can locally evaluate with my key. And if I add it up with what the other party evaluated, then I get the output, I get actually f of X. And then succinctness, I want the shares not to be too much larger than the function description. Of course, if I just give you like a function that can just be described with its truth table, then that doesn't mean much. But if I have like very specific function classes, then we typically have efficient like short descriptions. And then I also want to have like short keys. They should not scale with the domain size. And the simplest example, you can think of just like a linear function. Assume you have like the function is indexed by a vector, and you just want to compute the scalar product. And then with the last slide, it's very easy to do so. You can just secret share the vector that defines the function with additive secret sharing. You can just give the shares to the party. And then because of linearity, you just basically evaluate the function. So eval function is just a function. You add the two up and you get the output of the function by linearity. But of course, for more complex functions, that will not do. That's something we know. And just to say here, so what we got here, we got succinctness. The size is really just the size of the description of the function, this y, instead of the size of like writing this out for every element for the compute truth table. And now let's look at it like pictorial. How does it look like? So we have the succinctness. We want that these keys are shorter than, like, say, if we have if X is a bit string, shorter than the possible number of bit strings. And so if we look at the keys and we evaluated every possible like output, then what we get is this kind of expansion that we have here. And the second thing is additive reconstruction. So if I look at one specific point here, I can evaluate on the left-hand side, on the right-hand side for one specific point X, then I will get the function value f of X. And this now already looks similar to what we want. And this is, of course, no coincidence. In some sense, we're almost there. So let's recall our function. So let's call the requirement. We want a PCG. If we expand the left-hand side and they expand the right-hand side, then it should be in the correlation. And the correlation, like we can consider, this is a bit easier to write. So let's think of this. We have AC0 and BC1 such that A times B, whole by the left party and by the right party, equals C0 plus C1. And how can we compress this? So first of all, A and B are easy to compress. A and B, like we just went many random tuples. So like we know how to compress long, like randomness. That's the pseudorandom generator that we have. So we can compress these many values A and many values B just using a PRG. And then this comes from what we like from a warm-up exercise. So we have SA here and SB, just that now the parties have different seeds. Now the difficulty is, yeah, how do we get the C part? But you see that this is very convenient. We have here a C0 plus C1, and we have here also a plus on the left-hand side. So what we will do is we can just share C0 and C1 via the FSS for a very specific function class, namely the function class that consists of all functions that have this form. They take a value x and they map it at the x position to ax times bx. So evaluating the PRG, looking at the x position, and then both for both of these values. And yeah, and then we will get here f of x will be ax times bx. And so I hope it's easy to see that we have correctness. I can actually use this. So because we have we have here this plus this, so this will be C0, this will be C1, and this at the x position will be ax times bx. So that's exactly what we want. And it's also not too difficult to see that this now gives all the required conditions, just because the PRG is pseudorandom, and we have the secret sharing property that even if I know if I'm given one share, I cannot like learn anything from the other share except that this function is in the function class, which is something we're okay with because this is just defining the correlation. And so to recap, what we have is we take a pseudorandom generator, we take a suitable function secret sharing scheme. So we need a function secret sharing scheme for this class here on the right. And we get a PCG, and I showed it for Oli, but basically for all kind of correlations that have this additive structure on the right hand side, can also be higher degree correlations. That of course affects the FSS, but let's ignore that for now. And I can even do more if I start with a PRF instead of a PRG, where I can evaluate just point by point. And I have exponential or at least super polynomial stretch and a suitable function secret sharing scheme, then I get the same properties basically for the additive correlations. And this is something actually something special, because while PRGs generically imply PRFs, that's not the case for the right-hand side, because here it's not that the C correlation is the same than the output correlation, at least not for constructions that we know. And now the problem with this is, so this is great, we know how to construct PCGs, but this will be expensive, and the goal of this work is to get something that you just run and it's very fast, and this has bad concrete efficiency. So I just looked this up in a like kind of in an old paper. If you instantiate, and even like we did some optimizations, if you do LWE base, you have to start with like, this is actually for authenticated beaver triples, but you have to start with like a lot of key material, and the expansion time to expand it was like 8 hours or something like that. So you can do it, you can still run it, but it's not where you want to go. And so the question is, how can you construct concretely efficient PCGs? So what we started with were PRGs in some sense, and then we chose a suitable function secret sharing scheme. But what I would say, like actually, we understand PRGs much better than function secret sharing scheme. That's something that we know like much longer time. So what what we did is like kind of started from the other way around. So we start with the like efficient FSS, which is only known for very simple function classes. And then we look for a PRG that kind of satisfies the requirement that it can be evaluated, that it can be shared by this function secret sharing scheme. And so looking back at the slide, you already saw. And what we will do, we will like slightly simplify it. So we will forget, we will just say f of x is just a of x, is just ax at this position. And then all we need is a function secret sharing scheme, basically for the function that just evaluates the PRG and looks at the x position. And if we have a fixed b instead of like b to b1, which is of course not so interesting, and then this we can basically do it the same way. And this already gives, for example, vector OLE and also subfield vector OLE, which as was even in a talk this week, implies OT. So this already gives a lot. And you can also do higher degree correlations, more costly. So this is not generically, but this will be the case for what we're doing. And so efficient function secret. So we have to look at like what efficient function secret sharing schemes do we know? And efficient function secret sharing we know is, for example, point functions. So point functions are very simple functions. They're just non-zero at one point and zero everywhere else. And what you see here is not actually quite an FSS for a point function. It's just a punctured pseudorandom function, but this will be enough for a lot of context. And I don't want to talk about it so much. I just want to point to pictures to kind of give an idea why point functions are easier, because then we can use this nice tree structure and have just this one point that distinguishes that is different for the two parties. So point functions are FSS friendly. That's good. On the other hand, point functions are, of course, very, very far from pseudorandom. If you look at it and you almost always get zero, you will not believe that this is random. But it turns out, with what we've seen so far, with the function secret sharing schemes we have seen so far, linear functions and point functions, that's actually enough to construct a pseudorandom generator. And how this is done is with the learning parity with noise. And so learning parity with noise is basically the assumption that if you look at noisy code words and you add sufficiently much noise to like a linear code word, then this will give something random. So what's bad for coding theorists is good for cryptographers. And how does this give a PRG? How can you view this as a PRG? Well, the code is described by a generator matrix. That's a public matrix blue here. So this is just a linear code. Just think over F2. And then you multiply a message. And of course, you can recover linear algebra if you just have this. But it turns out, even if you just add not even so much noise, then you get here you have, but then you get something random. And well, this is function secret sharing friendly because the message this will be short, so we can just use additive secret sharing. So even if it scales with the length of the message, that will be short. And we can just share. This is just, I mean, there's just a few, it's relative, but a few non-zero noise coordinates. So each of them we can just share as a point function. Like a unit vector is basically just a point function in some sense. And then everything else, like here, everything else is linear. Like these are just linear. So this is just all handled with the very simple linear kind of property of additive secret sharing. This has some limitations if we just do it like this. So this is limited to quadratic stretch, and this matrix vector multiplication is expensive. Why is this expensive? Because we want to generate a lot of OTs. Think of, I don't know, 10 million OTs, even 100 million, and then your dimensions. So this is the size of the green here. So your matrix will just have like huge dimensions. And the limited to quadratic stretch you can overcome simply by going to the dual version. So what you can do is you can multiply the left kernel, just the dual matrix, and you get this, basically gets rid of the secret. Then you can increase the size of the secret, and then you can get arbitrary polynomial stretch. So the reason on the left-hand side why it's limited to quadratic stretch is if you choose it too sparse, you can just guess sufficiently many non-noisy coefficients, and again just do Gaussian elimination to get to the secret. And this is already nice, but this doesn't solve the second problem of this like huge dimensions. Now I have like still a really large dimensional matrix, and there has been like a lot of work into improving efficiency by using LPN, dual LPN with some structure that make multiplication faster. And so what we have now, this is like kind of the end point of the tutorial. We know if you have a function secret sharing scheme for point functions, you can get that actually just from minimal assumption one-way function, which gives you that, and together with structured LPN, dual LPN. Then you get concretely efficient PCGs for both the OT, and you can also do more, but then the concretely efficient, it depends what kind of secret you look into. And kind of a bit the starting point for this, or like kind of the state of the art are the silver PCGs, which are really very, very, very fast. But they come with a number of disadvantages. So they're non-parallelizable, or that at least the structure makes it non-trivial to parallelize. It's only experimentally verified, so we don't have a clear understanding of the security from a theoretical viewpoint, and it does not extend to pseudorandom correlation functions, so or like efficiently to degree 2 correlations or more. And what I want to take the rest of my time.
What do you mean that this doesn't have a theoretical analysis? So is it heuristic assumption? Or?
It's basically experimentally like looked that it has good minimal distance, but there is no kind of proof, for example, that it has good. Yes, so I will talk a bit about more, then I can also answer the question. But yeah. But very, very cool and very, very fast. Just I don't want to bash that here, just to be clear. And yeah, so now the rest of the talk, I want to talk about PCGs from expand accumulate codes, which is new kind of codes we introduced, and or like how to construct, in some sense, even better PCGs and PCFs.
Just a quick question.
Yes.
In techniques with persistence and variance of techniques, sometimes we assume extra structure in either the generated matrix or H. And for the most part, we do that just save space, like when you store it, but it could be used to speed up multiplication as well.
Yeah, so we also look at like kind of what is known. So this also in previous works, and kind of like having the structure for better multiplication. But thanks. And yeah, so exactly for this point. So thank you for the comment. The opportunities we have for optimizing PCGs is we can either improve this matrix vector multiplication, or we can improve the function secret sharing scheme. And in this work, we did a bit of both, like mostly improving the matrix vector multiplication. So I want to focus today on this, and that's a trade-off, of course. If we have more structure, it's always like in crypto, right? We want more structure because that makes things nicer, but that makes things also easier to break. So like warm up, what's an easy way to speed up matrix vector multiplications? Well, if you just have less entries, right? If you have something very sparse, will be easier. Just have to look at like a couple of entries. What goes wrong if I choose my matrix very sparse? Yes, yes, exactly. So if I choose it too sparse, then of course my output will be biased towards zero. We have the same problem as for the point functions. Then that's not convincing. And so kind of what we did is the easiest thing what you can do is we take sparse matrix, actually quite sparse matrix, and then we accumulate it. So what happens when you accumulate it? If you look at the first row here, let's say this is a very, very sparse matrix. And then by accumulating it, you get something like this. It's not sparse anymore. So the thing is, if I plug it in the before construction, before I likely didn't hit any of the noise positions. Now I will, because I'm better. I'm not sparse anymore. And what do we gain with this? So what do we gain with this compared to just using like a random matrix, like where we have LPN, it's very well understood. So we have this one part that is parallelizable and cache friendly. So this is, I didn't talk much about the FSS, but this is like somewhat straightforward to get it. And I mean, accumulating, this is very simple thing you can do. And then if you look at the overall computation, if you multiply the sparse matrix, you always just have to look at a few entries. It's not cache friendly, right? Because there will be far in memory, but it's always just a few entries. And so what we call this, or what we get is offline, so-called offline online PCGs, where you can run them in a slightly different fashion, where you first expand to offline seed, and then the first part is in the offline phase, and the second part is in the online phase. And so we always push work from the online phase in the offline phase. Why would you want to do that? You might not always want to do that, but if you really want to start, like if you want to be very fast, then you get an offline phase now that is really, really fast. You will see numbers later, estimated numbers, but numbers. And the online phase now has a low output locality. And because in this information theoretic protocols for the online phase, usually communication dominates, you can use the idle time for computing the next topic. And of course, that very much depends on like that very much depends on your setting. And if you have time beforehand, yeah, sure, run it beforehand. But this is like this might be a very attractive mode also to run it depending on your application. And so just why did we kind of invent a new code? Why didn't we look at literature? So we did look at literature, and compared, so I already mentioned like Silver, which is very, very optimized to be cache friendly. We kind of started with the so-called repeat, accumulate codes, and there you get something that is parallelizable. So that's nice, but it's not cache friendly. So this is, you can view this is also kind of the starting point of this. And what's also nice is that this gives us something like, first of all, I hope you agree that this is like super, super simple. This is like a very simple thing you want to do. And it also allows us to go beyond PCGs. What does it mean beyond PCGs? Like if I just have dual LPN, I'm limited to polynomial stretch, because if my matrix gets super polynomially large, well, that's something I cannot do. But if I look at here, so if I just look at this, now for every output entry I have to compute, I just have to look really at a few entries in this matrix here, and a few entries like just the noise vector. So this gives me, I can view this also as a PCF, when I just scale up dimensions. So just talking about something that I can still compute without being obviously broken. And is it FSS friendly? So FSS friendly is less clear, because this accumulate, if I know where my noise positions are, I can use them. But if I distribute it, I don't know where these noise positions are. So this is not obviously FSS friendly. But what I can do is I can just do it, accumulate kind of before, not as a matrix multiplication. Then this will just be interval. This will just be kind of interval noise functions. And yeah, if you have paid attention earlier this week, then we know that interval functions are actually function secret sharing friendly. And so you can just use this interval function FSS to share these interval function also based on one-way functions, very simple construction. And then have only, like, because your matrix is sparse, you can scale that and get a PCF. And yeah, now I already clicked that, but I was talking a lot about what we can do. And of course, the obvious question is, and I maybe said not trivially broken at one point, yeah, but that's of course not good enough, right? We want to have some trust that this is actually secure. So why do we should we believe this is secure? And so typical desirables, of course, we have our like repertoire of standard assumption, like they're around for a while. They're commonly used and not known to be broken in some sense. So it's very important that we use assumptions that we have like a lot of confidence in, but as also Yehuda said yesterday, they're not, in some sense, it also changes what our understanding of standard assumptions is. So unfortunately, we don't know a reduction for EA-LPN to standard LPN, for example, where you assume this to be random, but this is, and if you just see the slide, you should of course, this is a very bold statement, but this is like the simplest candidate for fast dual LPN friendly code, and hopefully might become standard in the future. And this is why should it I still haven't said anything, a word about security. So how to analyze new assumptions. So we should know at known attacks, right? This is not good enough, but at least we should look at known attacks. And all the like, this is just a list of common attacks, and a lot of like the most important attacks that apply to LPN style attacks can be cast in this linear test framework. So Gaussian animation, statistical decoding, yeah, you can information set decoding, DKW, and they can all be framed in the linear test framework. And what we had the discussion shortly. So basically, to show that something like a dual assumption resists linear test, you should look at the code generated by transfers and show that it has good minimum distance. So this has been folklore, and I think it was formally written down in the Silver paper. And we can actually show this. So we have a theoretical analysis where we can rule out attacks in the linear test framework, which does rule out a lot of attacks for Bernoulli sampled matrices. So every entry of the matrix is sampled independently at random with some small probability. And if you choose this, like, if you choose basically logarithmic n, where n is the output length, many non-zero, you already get close to optimal minimal linear distance with close to 1 probability. If you want to get like negligibly close to 1, then you can do with log squared. And for nonlinear attacks, so for example, Berlekamp-Massey, or like projecting onto a subring, these do not, so the Berlekamp-Massey needs like the algebraic structure that it doesn't have for the Aroba give. We're not in the, even if you use it with regular structured noise, we're not in the kind of regime where it applies. And for projecting into a subring, you have to be careful. This, I haven't said, I have only talked about F2. I said this also generalizes to larger fields analysis, and it's also plausibly true over rings, even though we don't have the analysis. And this, of course, doesn't mean that there's no other attacks, but this is kind of like some theoretical foundation of why we believe this to be kind of a good assumption. And for concrete efficiency, what you get, it's really, I mean, compared to 8 hours, it's pretty good now. So we get approximately 100 millisecond for 10 million random OTs. So to kind of expand the seeds. This is So this should be OTs, of course, large T, autocorrect. And that can be sped up by a factor of like approximately K if K processes are available. This is a theoretical analysis though. So this is estimated numbers, should be taken with some grain of salt, but saying like, you can do this fast. And in the online phase, it depends kind of on the assumption how sparse. Of course, like for efficiency, you want to choose the matrix very sparse, but for security, you want to choose it very dense. If you choose it completely dense, then you're back to standard LPN. So this is like a trade-off. With our theoretical analysis for this kind of numbers, we can get around with 40 lookups in the online phase and then adding them up and hash them. And for experimental, we conjecture that you can go down to as far as 7. We have some experimental analysis, but this is purely heuristic again. And the idea behind is it's actually not, you don't need to have good minimal distance. It's good enough if the adversary cannot find like a low weight vector in the code. So this is like pseudo distance. But yeah, this is the disclaimer. Of course, there's this trade-off between security and efficiency. And this is like a new assumption, and especially the aggressive choice. I mean, all of that, please go ahead and try to break it. And the aggressive choice of parameters needs to be like, what exactly is the right choice needs to be further investigated. But what we get is function secret sharing. If we start with function secret sharing for point or for PCF's interval functions and use this expand accumulate LPN pseudorandom generator, then we get concretely efficient PCGs, PCFs for Vole, OT, and more. And so there's a more exclamation mark. So especially in particular, we get circuit dependent correlations with work log square n times n instead of like n squared, because basically, yeah, ask me if you're interested. I'm happy to explain. And this is something that we didn't know before, because like Vole OT is kind of a degree 1 correlation because you can view it as Vole subfield Vole. But as soon as you go to degree 2, you kind of like, you have to do like a tensor product, and then you get this n squared or even worse. And here is because you kind of can push everything except for the sparse matrix together, we get this. So this is something very nice. And like if you just look at, I just want to like say this in this is, we just changed the code, right? Everything else that you could do before, you can still do. If you want to have Vole OT, then you get a very nice 2-round setup. You get a log n round setup for more general correlation. So all of this like still holds.
When you say circuit dependent correlation, do you mean bigger triples, or what is circuit dependent correlation? So
that you can kind of like reuse that you have the same randomness across different bios. Yeah. And yeah, also it also extends to beaver triples, even authenticated beaver triples, because the MAC again comes kind of for free. So this degree 2 in the
So it extends efficiently to beaver triples over a certain field.
Yeah, this changes your assumption that field you're in, so the field you're in, but the security analysis extends to larger field, and see it seems like minimal distance. Like, yeah, in some sense, intuitively should only get better if you're over larger fields. You can do it just, and you have a different assumption. Yeah. And even over rings, you can use it, but as I said, they're without the theoretical. And so to summarize, general tutorial part summary. So preprocessing is one of the main bottlenecks, I'd say, to practical MPC, and also hurts. No, silent preprocessing. The silent preprocessing via PCGs can save orders of magnitude in communication, and making it very, very efficient, the offline phase. And if you look at PCGs from expand accumulate LPN, so you get parallelizable cache friendly offline phase. You get more than you got before, for example, circuit-dependent correlations, both PCGs and PCFs. And we have some backing of the EA-LPN assumption, at least for the conservative parameters. And yeah, I have not talked about this at all, but we also did some optimization of the offline phase, basically reducing the number of calls to model as a random oracle for the construction, the FSS construction. It's not really the FSS construction, it's like punctured PRF, and the same for interval function, but it's very useful for this context, can also be used in other contexts. And yes, so this is appear at Crypto 2020. And thank you very much for your attention.
Questions? Yes, Shai.
About concrete parameters. So in the LW learning L's world, a few brave souls that try to attack it and combine different attacks in different ways and try to get the best performance of attacks and then use it to derive concrete parameters. Is anything like that exists in the LPN world? Other people that try to break?
I think so. I have heard of some efforts because this actually people are interested in using this in practice to make kind of like make incentives and suggest concrete parameters and then have like people look into it and break it. But in this regime we're looking at, I think this is kind of from the parameters a new regime to look at. So I don't know about, like, people have looked, like partly there's some papers, but I don't know if like a very organized effort in this direction. But I hope there will be.
More? Yeah.
Yeah. So since these are new assumptions, do you have any advice for how we should gain more confidence in them? And yeah, what would be the strategy?
I mean, incentivize as much people as we can to break them, right? If someone has money to spare.
Are you giving a bounty?
I personally don't have 100,000 to put down on that.
Just sell it to some company that will put $1 billion.
Exactly. have any of the 1,000 blockchains out there base security on it? I mean, that would be worth $1 billion. And then when they get broken, you hire parameters, make a new blockchain. It's very, very cheap these days to build blockchain.
Okay, that sounds like it.
So there's a plan, right?
Let's thank Lisa again.